In this video, we learn how to compute mean values, in particular, mean values of continuous functions. And if I think about this, I can immediately come up with many applications where this might be important. So here are a few. For example, what is the mean number of bacteria in a cell culture over one day? Or what is the mean drug concentration in the blood of a patient? That is very important information, of course, in the clinic. What is the mean sun exposure of a plant in a forest? Right, that's important. And also, what is the mean gene expression level in a cancer cell? These are all very important questions, so it would be good if we are able to compute mean values. And this is actually rather easy and directly related to the integral. But let's start with some discrete measurements. So assume I have measurements at times x1, x2, up to xn. And the measurements are f of x1, f of x2, f of xn. And so the mean value is, or the average value is, the sum of all the f's and then divided by the number, how many we got. Right, so f average is the sum f of x1 plus f of x2 and so on, divided by n. But now let's be a little bit more precise and maybe take uniform intervals between the time steps. And then the distance between the time steps is b minus a over n, where a is the starting time and b is the ending time, and then I have exactly n measurements between b and a. And then the xi's are a plus I delta x, so I start at the initial time and then I increment by delta x I times. Okay, so then the above formula can be rearranged a little bit. So from here we can find n. So then n can be written as b minus a divided by delta x. Now this then I can use and sub in here into this n. So let's just do this just for fun. So then f average is equal to f of x1 plus and so on plus f of xn divided by b minus a divided by delta x. So I get delta x divided by b minus a times f of x1 plus f of xn. But now you might think, well, we have learned about the summation sign. Why don't you use it? Okay, let's use it. Let's use the summation sign. So then I can write this to be 1 over b minus a, and then the sum I equals 1 to n, f of xi, right, the summation index becomes the index inside the f's, times delta x, which is a common factor. So I can write it like this. But now you might think, wow, this looks like a Riemann sum, doesn't it? It looks like a Riemann sum. And in fact, it is. So this is a Riemann sum. And so what happens as n goes to infinity? We have more and more measurements, we let n go to infinity, and then the average becomes this. Limit n goes to infinity of 1 over b minus a, sum I is 1 to n, f of xi delta x. And the b minus a is just a factor, 1 over b minus a is just a factor, and the rest is a Riemann sum which converges to the integral. So we get 1 over b minus a, integral from a to b, f of x dx. This is a cool formula. So let's write it down on the next slide. So the average is 1 over b minus a, integral from a to b f of x dx. So here's an example about gene expression. As you know, cells go through a cell cycle, which has like the G1 phase, the S phase, the G2 phase, and the M phase. And there are some cycling proteins or cycling genes which are expressed differently in different parts of the cell cycle. And so here's one curve on the left of one of these genes, how it is expressed during 2 cell cycles of a yeast cell. And this gene expression level can be described by the function given here, the function e. The cell cycle length is 300 minutes, and the time units is minutes. So what is the average gene expression of these yeast cells over one cell cycle? So what do we have to do? We have to compute the average according to the formula. E average is 1 over b minus a integral from a to b e of t dt if we are looking at one cell cycle, we could start at time 0 and end at time 300. So then b minus a is 1 over 300, integral 0 to 300, and then the function e, which is 1 plus 0.8 sine of pi divided by 150 t minus 120 dt. So here we have a beautiful integral to solve, and we cannot find an antiderivative directly, but we can use substitution. So we substitute u to be the thing in this sign, so u is pi divided by 150 t minus 120. Then du is pi divided by 150 times dt. But we also need to transform the domain boundaries. So then if t is equal to 0, which is the lower limit, then u becomes pi divided by 150 times minus 120. And then this can be simplified, which is minus 4/5 pi. And then if t is equal to 300, then u becomes pi over 150. So sub in 300, we get 180. So this is 6/5 times pi. So then we can do the substitution in this integral. I'm running a bit out of space, so I do this on an extra page. So here's the formula again, and I sub in what we just substituted. So then we have 1 over 300. The lower limit became minus 4/5 pi. The upper limit was 6/5 pi. And then the 1 is the 1, 0.8 stays, sine stays, but inside the sine we have u. dt is right here. So dt is 150 divided by pi. So then this times 150 divided by pi du. So now we have an integration of u, but maybe let's first work with the constants. 1 over 300 in front and 150 divided by pi here. So together this is 1 over 2 pi. And then we integrate, so we get u minus 0.8 cosine u evaluated between minus 4/5 pi and plus 6/5 pi. So we can sub in those numbers for u, evaluate the integral, and you will find that you get actually the value equal to 1. So the average value seems to be equal to 1. So meaning after all this we get equal to 1 right here. So let's look at the graph. So here's a graph. If I draw a line, e is equal to 1. Yeah, it looks like the average, right? It looks pretty much to be in the middle. So the mean value satisfies a wonderful mean value theorem for integrals. So this says if f is continuous on AB, then there is a number c which attains the average value. So f of c equals f of average, which is equal to 1 over b minus a, integral ab f of x dx. So this can be visualized graphically very nicely, like down here. So you see the blue curve, and the area under the curve is the integral. And then the mean value or the average value is the red line, and there's one intersection right here. So the function on the value c is equal to the average value, equal to the red line. Here on the right is a different function, and this actually happens twice. So here the function is equal to its mean value, and here the function is equal to its mean value. So this point c is not unique. You can have many of those points, but they do exist. It's cool. And this has a wonderful interpretation. So look at the red formula again for the mean value theorem for integrals. Now if I multiply this by b minus a, then I get the blue formula here. But now this has a very specific meaning, right? If f is a positive function, then this here is the area under the curve. And the left-hand side has also an interpretation as area, right? It is a rectangle. So it's the area of a rectangle of height f of c. And f of c is the average. So we can find a rectangle which has the same area as the area under the curve. And this is again shown here. So the gray shaded region is the rectangle, The blue shaded region is the area under the curve, and these areas are exactly the same. Isn't that cool? Let's do that for the gene expression example. So for the gene expression curve, find a value c so that EC equals the average. So what we are looking for, you can see already in the graph, would be, for example, this point, where the function equals its mean value, and the mean value was equal to 1. So what we need to solve is 1 is equal to 1 plus 0.8 sine of pi divided by 150, and then the value c is the unknown value which I'm interested in. So for what value of c do I hit the mean value? And so the 1 cancels, the 0.8 is non-zero, so this basically means that the sine of pi divided by 150 c minus 120 has to be 0. And then this is satisfied if c is equal to 120, right? If c is 120, then inside the sign we have 0. So 120 is a point right here. So we found a value for c so that E of c, so then we get E of 120 equals E average, which was equal to 1. So we can do that. A mean value of a continuous function can be computed as an integral 1 over b minus a times integral a to b f of x dx. And the mean value theorem for integrals says that there's at least one number c so that f of c is equal to f average. Yes? Hey! Yes, it was nice indeed. Nice to meet you. You are leaving? Bye-bye!
Mr. Sun came up and he smiled at me.